Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Marc Buie with us today. Hello, Marc.
Hi, it's great to be here. Thanks.
Well, thanks for agreeing to talk about your very lovely article, which we will get to here in a second. And Marc, what's your geolocation?
Well, today I happen to be in Boulder, Colorado.
Okay.
Might see some austere walls on my office here. We've just moved into a new place.
Oh,
And
cool.
I haven't got my artwork, including my nice picture of Pluto and Arrokoth on the wall yet.
Well, congratulations on the new building.
Uh,
Let's see. It is October 17th of 2024 as we record this. So we're past equinox and you're in Boulder. So I imagine the trees and the aspens are doing their color thing.
yeah, our ash trees are starting to get pretty nice looking, and there's snow coming in the mountains this weekend.
Do you ski?
Oh, I can. I prefer the water kind, not the snow.
Ah. Okay. Well, let's see. I am in Phoenix and we actually went below 70 degrees Fahrenheit this morning.
I brought out the
That
parkas.
was kind of a yay. We'll still get up to around the upper 90s today, but overall it's starting to cool down, so it's really great. So good.
Well, having lived I went to school in Tucson, so I know that climate pretty well. And this is a magic time of year in southern Arizona.
Yeah, yeah, it's very nice. All the snowbirds start coming down, so it's
Yep.
all good. And Marc, what do you like to do for research?
Well, my research dominantly is focused on the outer solar system. I've done a huge amount of work on Pluto, which is probably no surprise since I'm involved with the New Horizons mission.
Yes.
And then as we were learning more about Pluto, I transitioned into the Kuiper Belt and was part of a big survey to find lots of Kuiper Belt objects. And
Mhm.
so when New Horizons needed to find another target past Pluto, my name came up, bubbled to the top of the list for somebody to help the project out with that project.
That is awesome. So we are going to hear this one straight from the source, people. And here we go. So let's bring up this very awesome Planetary Science Journal article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. The New Horizons extended mission target, Arrokoth, search and discovery. And Marc, take us away.
Well, first of all, I realize this is kind of an unusual paper.
Hmm?
This
It is.
the culmination of the work reported here was completed 10 years ago.
Hmm?
The work began 20 years ago. You
Okay.
might think, well, I'm kind of being kind of lazy and not getting the research out quickly enough, but we had a spacecraft to run, and
Mhm.
getting the spacecraft there was far more important than getting the paper out. So
Yes.
those deadlines just kept beating on me. And finally, after we finished the New Horizons flyby of Arrokoth, I finally had enough breathing room to pull this story together.
Cool.
So this paper was took 20 years start to finish. And the first 10 years of that is doing the work. And the last 10 years is kind of pulling it together and turning it into a paper worthy of publication.
Cool. Thank you so much for doing this.
And you can see from the first page here the list of co-authors. Um, these days, these projects, they're not done in a vacuum. There's a lot of people that help make
Oh,
these
yeah.
projects go. Um, from myself, kind of doing most of the work on these things, to project management and other people helping with different aspects of the software data collection. And if you know some of these names, like Matt Mountain, he's on here because at the time he was the director of the Space Telescope Science Institute,
Yes.
was very helpful. He and Neil Reed, a little further down the list, were very helpful in coming up with solutions for how to get Hubble involved, which you'll hear about as we go through the story.
Very cool. Very cool. Okay. Let's go ahead and get into it.
Well, okay, so why were we doing this work?
Mhm.
The reason for it was we had a perfectly good spacecraft. We had some fuel left over after Pluto, and we wanted to go and investigate further out in the Kuiper Belt, further out from the sun from where Pluto is.
Uh-huh.
This is a research topic that was highlighted by the most recent, at the time, Planetary Decadal Survey Review, sort of
Hmm.
a census of what we should be doing in the future.
Hmm.
And at the time we launched New Horizons, we did not have a target to go to after Pluto.
Hmm.
So it was a real hard sell to say, we're going to build this spacecraft to go somewhere we don't know where we're going, but give us the money and launch it. So the way it worked out is Pluto, we knew about it, we knew where it was, and we knew we were going to do a lot of great science, and that was the primary target.
Yes.
But in terms of some of the more foundational breakthrough research was going to come, we knew, from the Kuiper Belt. Um, but we figured, okay, we're kind of still early in finding Kuiper Belt objects, and we don't really know the full population. So surely there's something out there that we can go to. Let's
Surely.
go ahead and launch and just hope for the best. So this project started in 2004 with
Hmm.
what we call the wide and shallow search.
Hmm.
And at that time, the search area that we had to cover on the sky was quite large. And if you go down to the nice figure that shows
Yeah.
the galactic plane,
Okay.
this
There.
shows you what the problem that we were dealing with.
Woo.
These circles represent the search area for objects that have orbital parameters that are consistent with the objects we know in the solar system,
Okay.
that if you track those objects forward in time to um, um,
Okay.
the area that New Horizons will go to after Pluto, this is where you had to look in that year to find the objects that New Horizons could get to. And one of
Yikes.
the things you see here is that the circle is getting smaller and smaller and smaller, and it
Hmm.
was at its minimum in 2014. I'll
Yes.
talk about some of these later ones in a bit. But the thing to notice here is all this white stuff in the image. Well, those are just star clouds from the
Yeah.
center of the galaxy.
Man.
And nobody in their right mind would bother taking a big telescope, looking in this part of the sky for a super faint target
Right.
to send a spacecraft to. That's just way too hard. And nobody did. And so that means that there were no objects known in that region of the sky
Uh-huh.
horizons could get to because nobody's looking in that region. Unfortunately, Pluto's where it is, the launch was where it is, and this dictated where we have to look. And from a New Horizons perspective, we didn't have a choice of working in an easy region. So
Hmm.
we had to learn how to do the hard stuff. And that is just digging into these fields and looking at getting rid of the stars and then
Right.
finding things that are moving around in the object. If you
Wow.
scroll down, there's a figure, I think it's like maybe figure 2 or 3, which shows an example from a little bit later in the project that kind of illustrates just the kind of crazy stuff that we were having to deal with.
Three. Here we go. Crazy
So,
stuff.
yep, it's right. So here on the left is what the images look like straight off the telescope.
Okay.
And this is just a tiny, tiny little postage stamp
Yeah.
from the image.
Mm.
And the
Ooh.
first image on the upper left was taken at one time. 2 hours later, we take the image on the lower left, and we're looking for things that move.
Ooh. Yeah.
And it turns out those arrows that are on there are pointing to a main belt asteroid
Cool.
that we found in this image, and it's just an example. So
Mm.
we had to learn how to do things like building template images and subtracting them from the images. So you take away all the star clutter and
Yep.
hopefully leave yourself with an image that shows the moving object in there.
Okay.
By the way, this technique was when we first started doing this, there were very few people doing it, and the computers were not really fast enough to do this very easily.
Right.
But this is a foundational tool that is going to make the LSST survey with the Vera Rubin telescope work. This
Cool.
is exactly how it works. They will take templates, subtract it off, and look for all the moving things.
Nice. Very cool.
So At this point, that's kind of like old news, but back then, this was like we were inventing tools that nobody had ever touched
You were
before.
tried, yeah. So what is so we talked about the one on the left. Have you done a subtraction here in the middle?
Yeah, the images on them in the middle come from taking the template for the static sky and subtracting it. So
Okay.
that's why you see the object in two different places in the middle.
Yeah.
And on the right-hand side, that's a little bit more complicated, not really worth getting
Okay.
into so much.
Okay.
But it just illustrates the difficulty of working with these objects.
In the crowded fields, yeah.
By the way, if you happen to know anything about what magnitudes mean, the images on the left are seeing objects down to about 25th, 26th magnitude,
Yep.
which is pretty faint. And the asteroid that's in there was probably around 23rd or 24th magnitude.
Okay. All
If
right.
we were looking at the galactic poles, we wouldn't need to do any of this nonsense. We could just take a picture and boom, there it
Boom,
is.
be done. Right. A little more crowded.
So the wide and shallow search started in 2004. We didn't think there was a great chance that we would find an object
Okay.
in there just because we had so much area to cover. It took something like 100 images with a very large field of view camera to cover that whole area. And we covered maybe 80% of that.
Okay.
But to cover it that much of the area meant that we could only go fairly, it wasn't that deep.
Okay.
And the odds of us finding something of interest to New Horizons was pretty low. So, in fact, cutting to the chase, we were probably looking, the brightness ratio difference was about a factor of 1,000
Okay. Yeah.
at best away from where we needed to be. In other words, it would have been better for us to look 1,000 times fainter, and
Okay.
we would have had a chance, but we simply couldn't do that. That would have required something like 3 years of observing time in 1 month.
Wow.
And
Okay.
we only have the one telescope, so that was clearly impossible. But we didn't know that at the time. So we searched the area, we took a lot of data. There were a lot of mistakes made in the data collection process.
Sure.
There, I could go on, hours and hours about all the things that we learned there, but we did find Kuiper Belt objects. And I think it's in table 3, maybe, was a list of the objects that we found.
Let's go to table 3, search discoveries, indeed.
Yeah, there's the list of what we found. Now, our initial estimates there is that we should have found about 80 or 90 objects.
Okay.
So in the first, I don't know, it was 3 or 4 months, the Japanese collaborators are working on this. I had lists out, and we found these 35 objects pretty fast. But
Cool.
based on what we thought at the time, we thought, oh, we must be missing something because we should
Yeah.
be getting a lot more
Oh.
objects.
Mm-hmm.
So then I embarked on, it was 7 or 8 years worth of work to try to improve my tools, learn from all our colleagues, people that were kind of doing the same kind of work. But in the end, if you look at the right-hand column,
Delta V.
this is the magic number that matters for New Horizons. This is the amount of change of velocity you need to impart on the New Horizons spacecraft in order to get to that target.
I'm with you.
And this is in units of kilometers per second. So the bigger the number is, the more you have to kick the engine and push on New Horizons one way or another to get to the object.
What was the maximum? What was the maximum that New Horizons could do on Delta V?
Yeah, I was just getting to that.
Oh, okay.
The maximum in these units is 0.1.
Oh, goodness. Okay.
It was about 150 meters per second was
Yeah.
the amount of delta V that we thought we had to work with.
Yeah. Yeah.
And so you can see here that we have quite a few of them that just take way too much. And the
Way
best
balance. Yeah.
looks like it's around 1.1, and that's 2004 LW31 in the table.
Okay.
And we actually observed that one later on with New Horizons from a distance. But so we got some good data on it, but nothing like what was going to come for
Yeah.
Arrokoth.
Okay.
So this search did not give us what we needed, but in terms of finding objects, but it taught us a lot about how to
How to
find
do
objects
it.
like this and in these crazy star-filled regions.
Mm-hmm. Mm-hmm.
So we ramped this problem back up again in 2011.
Okay.
This is sort of the middle scale search in the next section.
Okay.
That at this point, we changed strategies. Up until this point, it was basically just me with a programmer, part-time programmer working on some of the software and the techniques.
Okay.
2011, we really upped our game. New Horizons is already off the ground. We
Yep.
need to find an object quickly. In fact, we knew we had to find it by 2014. So we only had 3 more years left to go.
Yep.
And so Alan Stern brought in a bunch of other people. I think the team went from 1 to 20
Okay.
almost overnight. And
Okay.
then we started using another camera in Chile at the Magellan Telescope.
Mm-hmm.
And so we began observing each year with a revised strategy based on lessons learned from the first survey.
Okay.
And that we did pretty well. We definitely were going fainter. All those lessons learned really did help. But the problem is, even though we're finding lots of objects, and I think if you go down to table 5,
Let's go down
maybe
to table
that's the one.
5. There's our search runs. Table 5. There's our figure 3 and table 5 log notes. Okay.
Yeah, that's okay. So maybe it's table 6. There, if go on to the next one,
Here
and
we go.
there we
Yeah,
go.
yeah. Table.
There's the list of the objects that we
Woohoo.
found in 2011 to 2014 with the Subaru telescope and the Magellan telescope.
Cool.
Now, you can see already this is a longer list than what we did before.
Yep.
And that is a pretty good way to quickly know that, okay, we're getting fainter. We're seeing more objects. There's more fainter objects than there are brighter objects. And the last column, this is the money column here,
Yep.
delta V, you'll
Yep.
notice I changed units on this table.
Yes. Yes.
Now it's showing meters per second. So
Awesome.
now we are seeing things that are closer for
Yes.
New Horizons. And remember, the magic number is about 150.
Yes.
And you see that and this is actually sorted by delta V
Mm-hmm.
on
Mm-hmm.
this table. And the best we did was 245. So we got within a factor of 2.
Yeah.
But, space is not a very forgiving place. And you can't simply go out there and put more fuel in the spacecraft. If
No.
you don't have the fuel, you can't, no matter if it doesn't matter if it's a factor of 2 or a factor of 1,000. It's just as
Doesn't
it is.
matter. You ain't making it.
But we knew we were on the right track. We're doing better. We're seeing fainter objects. The search region is getting smaller each year, as you saw from that first figure.
Uh-huh. Mm-hmm.
And it turns out that 2014 was when the search region was the smallest.
Cool.
So at the end of the 2013 observing season, we basically knew these results and realized, okay, we've done everything we know how to do with this equipment. And we don't have much time left. We basically have just another year left to find it. And we can't take a chance on us figuring some new miracle out.
Right.
So
Well,
at that time, the team decided all collectively that, the only way we're going to do this is to go to the Hubble Space Telescope.
okay.
And we had not gone that way before because one, this is a very, very expensive resource to tap into.
Yep.
You really have to demonstrate that there is no other way to do it. That's kind of the rule of using Hubble, is if it can be done any other way, you have to do it that way. And even if Hubble makes it easy,
Right.
it has to be the only game in town. But we also had a problem that normally the way Hubble works, you put in a nice proposal. If everybody likes you, they give you time. And then a year later, you observe. And this was January of 2014. We're having this conversation. And if we had to wait an extra year, it's game over already.
It's gone. Mm-hmm.
So we had to begin working with the Space Telescope Science Institute to find ways of, one, getting approval for the project of searching, designing what the search project would look like,
Yeah.
getting everybody to agree and line up. And it turns out that the survey that we needed to do was going to use something like over 200 orbits of Hubble time. Now,
Okay.
that's the coin of the realm for Hubble, is they give it out in one orbit chunks. So
Right.
Hubble takes 90 minutes to go around the Earth. You get to observe your target for about 40 minutes out of that time, and then you just sort of add it up.
Yep.
So this figure here that we're looking at
Okay.
is this search region that we were covering. And just imagine that ellipse that you saw in that other figure against this Milky Way.
Oh, yeah. Mm-hmm. Yep.
This is that same ellipse
Okay.
covered up, and each one of those squares represents the footprint of the wide field camera 3 on Hubble.
Mm-hmm.
So for two orbits is sufficient to cover one of those blue squares.
Okay.
And so you basically try to do these orbits back to back, or if you have to, you could skip one orbit, but they're supposed to be close in time. And what we're doing is tracking the objects that we think are there.
Mm-hmm.
And so the stars are trailing all over the place. And then the Kuiper Belt object that we're looking for would be holding still.
Okay. Okay.
And then we had to, you search in through the data looking for a faint object in there.
Mm-hmm.
So there's blue squares and there's green squares.
Yes.
And the difference between those two is that this was such a big request of time. So they decided to break it up into two pieces. One is a pilot survey,
Okay.
and the other is the full survey.
Okay.
The pilot survey was coming out of the director's discretionary time allocation. So
Yeah.
the director of Hubble was able to just give us that time and guarantee that we would get it. The other time had to go through the review process and get the community to agree that this was worth doing.
Okay.
But the condition was that during the pilot survey, we had to find two objects in the Kuiper Belt to vindicate our estimation of how many Kuiper Belts or objects are out there. If we didn't find any, they would say, you guys don't know what
into that.
And we're not going to give you the rest of the time.
Right.
But we had to do it very quickly. You couldn't just wait a year. So the work that we had done in all the previous decade, that you couldn't take that slow and cautious approach. And in fact, one of the more amazing things that came out of this was how Space Telescope Science Institute handled this situation.
Okay.
They didn't know whether we were going to be approved or not.
Right.
But they knew when the approval would come. And so the very next week, they decided for that week, and then I say week because Space Telescope is scheduled on a weekly basis.
Mm-hmm.
So you build a week's worth of commands, they get uploaded on Sunday evening, and then the telescope is busy for the next rest of the week, and then you work on the next week's commands.
Okay.
So this particular week after the approval could come, they decided to go ahead and develop two complete separate sets of commands for the telescope, one with our observations and one without.
Okay.
The last minute, they decide, we don't want to give you the time. This is not going to work. Then they would have these other commands there to keep the telescope busy and you wouldn't lose any time. So they did both, and they suggested this as one of the techniques to get this done.
Mm-hmm.
So Friday afternoon, we hear that the Telescope Allocation Committee says, thumbs up.
Cool.
Get your time for your pilot survey. Sunday, the commands get uploaded. Monday morning, I'm downloading data from these green squares.
Nice.
But the thing is, we didn't have any software, any tools other than just our wits and just general experience to deal with this data. It's not like we'd been spending 4 or 5 years building the tool so that we could just jump into it and process it.
Right.
We had to start on that Monday. And it was going to take 2 weeks to get all the data for the green squares.
Okay.
And by the end of the 2 weeks, we need to be able to tell them we found objects or we didn't find objects so that we could continue the survey.
Okay.
This is probably one of the most intense periods that I've ever had in doing research, is having that kind of time pressure on this. So we had 5 different independent groups, all with equal access to the data. And we had daily meetings to compare notes and see how we're doing. It wasn't like a blind test, but everybody was doing what they thought was the best thing to do.
Good.
I was one of those teams by myself using all of my tools.
Mm-hmm.
And it wasn't so much as a race. It's like, we're just hoping that somebody's going to come
Somebody
a
gets
way to.
one. Yep.
So it took me about 4 or 5 days to get a set of tools that could process the data all the way through. And I started to look for things and I'm not finding anything. And I'm wondering what's going on. So the beginning of the second week, John Spencer created some fake data, which
Ooh.
has, it's the images themselves, but he put in a fake image for a Kuiper Belt object according to how it should look.
Okay.
But he wouldn't tell me how he did that, so that I had to write my own software to be able to extract that.
Find it.
So it's kind of not a double blind test, but it was at least half blind.
Mm-hmm.
So I'm searching for his data early in that second week, and I'm not finding them.
Okay, bummer.
And kind of looking at the results that came out of that, I realized I managed to track it down. There was a sign error in one line of code. I was adding a number when I should have been subtracting a number.
Okay.
And as soon as I fixed that, all of a sudden I could find everything that John put in the images, which just jumped right out.
Right.
Then I had to go back and rerun my software
Right.
and
Less
looking for the objects. And so if you scroll down, I think it might be figure 5.
Let's go down. Figure 5. Yes.
No, next one, figure 6.
Figure 6.
No, the next one, figure 7.
All good. Figure 7.
There we go. That's the money figure.
Okay.
So this is a graphic that comes out of the tools that I wrote.
Mm-hmm.
So it's a little hard to see what's going on here, but there's 3 rows of images that you're looking at here. And these are tiny, tiny little pieces of the image taken by Hubble.
3, yeah.
Okay. You'll see there's red circles.
Yes.
In there. There's a row of, it's like, look in the middle, there's 5 red circles in the middle.
Mm-hmm.
And then there's 5 red circles on the bottom.
Yes.
Those red circles are in the center of a postage stamp from each of 5 images taken in that orbit. Okay. And then the next orbit, here's each of 5 images. Okay. Then what I do was searching, you have an array of velocities that you expect these objects to be in.
Okay.
And you just try a velocity, you stack up the 5 images in the middle, and that becomes the image on the upper left. Okay. And then stack up the images on the bottom, and that creates the image on the upper right.
Okay.
For a given velocity.
Yes.
And all of those stacks for all the velocities. And if there's a real object there, one velocity will have a really nice looking image. And that's what you see here is there's one dot right in the middle.
Yep.
And on the left, the red circle is saying, this is where I found a spot in the left image.
Mm-hmm.
The circle on the right is saying, if the image on the left is real,
okay,
there will be something in the red circle on the right.
Okay.
And for it to be in the middle of the circle means it's the same object, it's real, we know its orbit, and we know it is useful to New Horizons all at once.
Nice.
And so here I am scouring through these hundreds of images, and there was many thousands of these graphics that I had to look at, most of them which were just noise and junk that I could easily tell. And up until I saw this graphic, I still wasn't quite sure what I was looking for. I kind of had an idea,
Okay.
but the instant this graphic popped up on my screen, I knew we have a real object, we have a project, we're going to go to a Kuiper Belt object. This is
Ah,
this is going to work.
very cool.
And that is, in all of my years of doing scientific research, that is the only time you've ever had that kind of instantaneous moment of discovery.
Cool.
Every other research project I've ever done is something I call a dawning realization. You get some data and it kind of looks interesting. I wonder if it's right. I wonder if it's wrong. And you'd go
Yeah,
more work. And with each passing day, with each passing week or month, you become more and more um, sure that the result is good. This one, it was just a matter of a instant. I knew all of these things were working.
very cool. Very nice.
And boy, I tell you, that changed the tone of all of our daily conversations.
I bet.
Been looking for this thing for 10 years, and here's an object.
Boom.
Okay. So here, this is the
Amazing.
other kind of slightly humorous part of this story is that
Yes, please.
on this day that I found this object, it was just a couple hours before the daily meeting that we were going to have. I
Okay.
didn't tell anybody that I'd found something, but I
Ah,
just wrote this code that's in the top of that image, 1110113Y. That was
mhm.
my own nomenclature for how keeping track of these things. I just wrote that number up on my whiteboard and didn't say anything. People came into my office, sit down for the daily meeting, and they're looking over this. Oh, what's that?
Latest version number. That's what that is.
And then I showed them this graphic and explained everything, and everybody just kind of went berserk.
Woo.
So it was very exciting. But then I told Alan Stern, sitting across from me on the table, I said, Alan, this is going to be the object we fly by. And he was saying, no, 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 no. We're going to have a choice. We're going to have all these other objects to choose from. Keep looking. This is not going to
Sure.
be the one.
Sure.
But I said, no, no, this is going to be it. And I was right. First object we found in the survey is Arrokoth, and it's the one we went to.
But you did find other ones.
We did.
Right.
On the very next, so that day, we just took a break. We went and had a barbecue. Everybody's hanging out and just patting each other on the back. Hey, we finally succeeded. And now we have to kind of look at the rest of the data and just turn the crank. The next morning, on a Saturday morning, I'm sitting there and I'm standing there in the backyard talking over the fence with my neighbor and telling him what we had just done the previous night. And I realized as we're talking, I am not paying any attention to my neighbor anymore. In my head, I'm just thinking, oh my gosh, I have all these other images. I wonder what else is in there.
Why, maybe, yeah.
I told my neighbor, I said, look, I need to, we'll pick this conversation up later. I have to go to work. So I drove into Boulder from home
Okay.
on a Saturday morning and started plowing through all of these graphics.
Yep.
And inside an hour, I'd found the second one.
Cool.
And that's what we needed to keep the whole survey going. So
Yeah.
Saturday, I call them up saying, hey, we found the second object. Now we had to build the decision package to send to the Space Telescope Science Institute. On Sunday, we sent that in. They had a meeting and reviewed it. And on Monday morning, they gave us the approval to go with the full
Full
project.
survey. Very good.
So over the course of the next month, we were taking more and more of that data. We found a total of 5 objects in this survey. Out of those 5 objects, and I think if you scroll down
Yeah.
to the summary table for these objects, and I keep on going down there.
Let's go down. HST
One
astronomy.
more.
8. And let's keep going. Targets. Here we go. As our
There we go. These are the 5 targets. And you'll notice the delta V column, third from the right,
Aha.
still meters per second. now we have two numbers that are below our magic number.
Yep. 59
We
one.
knew for PT4 and PT5, by the way, PT stands for potential target.
Okay.
PT4 and 5, we knew very quickly that there was no way New Horizons could get to it.
Yep.
We never did any extra follow-up. We don't actually know what the orbital elements are enough to calculate a delta V, but we know that we wouldn't do anything with it.
Okay.
So we had two, PT1 and PT3 were the best two candidates. And there really was no choice, even though we went through the motions. You want to go with the one with the lowest delta V.
Almost, yeah. So you got room to move.
Fuel for the next thing.
Mm-hmm.
If we had done PT3, I'm sure it would have been a fantastic encounter, but we wouldn't have left any fuel for any future observations with New Horizons.
Right. Mm-hmm.
So 59, the magic number for delta V with PT1, that is the object that is now known as Arrokoth, and it was the flyby target that we went to on January 1st, 2019.
Yes.
And saw that wonderful snowman kind of shape in the images.
Yeah. Mm-hmm.
And the result of that effort is really just it's a very gratifying moment, or high point in my career just to have been involved with this. I think it's one of the most it's one of the biggest discoveries that and results coming out of the space program is to do this object. We know it's a contact binary. There's another paper that I wrote that was published a while ago investigating this object that showed it was a contact binary. New Horizons flies by and confirms that, but also we get clues about how these objects in the outer solar system are put together.
Mm-hmm.
This gets us all the way back to the very, very beginnings of the solar system, when things are accreting out of the gas and dust from which our solar system was born.
Mm-hmm.
And we haven't had data like that before. So it's, even though it took me a long time to finish this paper, it's we learned a lot from it. It was a really great exercise.
Awesome.
Just kind of in kind of wrapping this up a little bit.
Okay.
If you scroll down, I've got several appendices in the paper. The one I wanted to point out was one about the Ice Hunters project.
Yes, so there's some really awesome appendices, people. Check them out. And we will slide down here to Appendix C, the Ice Hunters, citizen science.
So over the course of this investigation, people started to realize the power of bringing in lots of people to help you. I think the first thing was Galaxy Zoo, that helped people helping to categorize galaxies in various images. And that's where Galaxy Zoo came from. And Ice Hunters was a project underneath the Galaxy Zoo universe there, if you will.
Yes. Yes.
And so here, there's some details about how we set that up. But more importantly is that if you scroll down, you'll see I list all the names of all the people that signed up for Ice Hunters and helped us out with searching through this data. So it's almost really packed in there, and it's almost a full page worth of names.
Yeah, so we'll go through that a little bit. We got a little bit here, and then we got a full double column on here from the B's down to the M's, and then we carry on with the M's and a whole nother column. So yeah, almost full page down to Zorpa.
Yeah, it was very popular at the time. The observers were, or the people that were viewing the images did a really great job. They were from all over the world. In terms of engagement and repeat activity, this one kind of set all sorts of records. The one problem with that is, at the time, the network and computing infrastructure was just not quite up to snuff.
Yeah.
And it turned out that with my software running locally, where I had access to all the data, myself and an undergraduate student that was working with me, we could go through all of the images in a couple of days.
Okay.
And ice hunters could do the same thing, but the problem was it took me something like 6 weeks to upload all the data
Ouch.
to the servers so that the ice hunters could look at it. And so that turned out to be an impractical way to do it
Mm-hmm.
just because of those communication timescales. I think
Yep.
if we were doing it today, it
Be better.
probably would work out a lot better.
Yeah.
But
Bandwidth
in any
stuff.
case, I'm still very grateful to everybody that helped out with that project and gave it a shot. And I think people enjoyed it as well.
They got a discovery out of it. It's very cool. Very nice. Beautiful, beautiful, beautiful.
So one of the things that this actually feeds forward into quite a few projects that I'm working on now,
Okay.
in both in terms of tools and techniques for investigating these objects, but also the scientific connections. I'm involved in the Lucy NASA Discovery mission.
Okay.
It's going to study Jupiter Trojan asteroids. And we think they're a related population to the cold classical Kuiper belts,
Okay.
which Arrokoth represents,
Yes.
except they've been subject to more collisions and more disturbances over time. And Lucy's going to go out and find all this stuff out. But with the successes that we had with learning about Arrokoth and what we could learn about it from the ground without the spacecraft, we're applying those same techniques to all the Lucy targets.
Mm-hmm.
And we found quite a few interesting things that we wouldn't have known without flying there that is helping with mission planning. Um, we already know that it looks like there is a genetic tie between the Jupiter Trojans
Mm-hmm.
and Arrokoth and the Kuiper belt, but we'll be there with our first flyby in the fall of 2027.
Nice.
And we will get more data. But this, as with any good research project, this kind of works us into the next thing and answering more and more deeper questions. And that's no exception to the Arrokoth work. And it's been a real blast to work on this kind of stuff. By
Cool.
the way, I've taken the concept of citizen science one notch further.
Okay.
Ice Hunters was good enough, but what we learned to do with occultations in studying Arrokoth and then now see
Mm.
occultations,
Mm. Yes.
I
I got them.
recruit from citizens or actually community members. And so we've now involved more than 1,000 people in doing occultation observations that had never used a telescope before.
Yeah. Nice.
Traveling around the world to study these targets. And I think going forward, there's a survey that needs to be done with this technique of cold classical Kuiper belt objects to see, is Arrokoth weird or are they all like that?
Right.
And
Right.
that's going to really be an important constraint on the
Formation.
formation models
Yeah.
that we are all working on.
Yeah.
Unfortunately, that's a big project. It takes a lot of money. It's mostly just to support the people to do these observations, but that's kind of one of the things that I'm working on. It's going forward is to try to find a way to how to do that sort of thing.
Super. Let me ask one question about New Horizons, since we did a Delta V there of 59 and we had 150 or so. So is there anything potentially to use that rest of Delta V with New Horizons to get another object?
Well, there is fuel left on board.
Uh-huh.
And of course, it's not 150 anymore because we use some of that.
90-ish.
So that means that we have less volume that we can access with the spacecraft
Mm-hmm.
unless we wait longer. Problem is that we've moved past most of the Kuiper belt that we know about.
Okay.
But we are still looking.
Yeah.
There's a command paper that came out very similar in time. First author was Wes Frazier, this is all from our search team on New Horizons. We haven't quit looking for new targets just because we found Arrokoth. We've been working on it since then. And the problem is there just aren't as many.
Sure.
We're getting out beyond the dense region. So the odds of finding something are much lower. unfortunately, than it was for Arrokoth. By the way, we estimated the probability of finding Arrokoth
I
to
was
be
going to
about
say,
85%.
okay.
Was not a slam dunk. And people were very kind of grumpy about that because they wanted to say no for sure that we would get it.
Yeah.
But unfortunately, the numbers that we're looking at for the prospects in the future are lower than that by a couple of order of magnitude at least.
Ouch. Ouch.
But
Okay.
you don't have a spacecraft and an observatory in the Kuiper Belt every day.
No.
And you have to work with what you've got. And if we don't look, we know what's going to happen. So we're looking just in case that we're going to get lucky and there's something that we can get close to. We took data even with the Subaru telescope this past year, and I don't have results from that. It's still, there's a lot of processing time involved with extracting this. And we're hoping that maybe we'll find something, though we're making other plans to take this search on to the Vera Rubin Observatory.
Okay. Mm-hmm.
Um,
Arrow.
Most likely, we're targeting 2026, assuming that it comes up to speed and gets operational
Like,
on time, which is looking pretty good.
mm-hmm. Yeah.
And then after that, we're looking to the Roman Space Telescope. I consider that to be a bit of a successor to Hubble,
Mm-hmm.
and we think that one actually has got an even better chance. But that's a longer wait to get there, and we don't want to just wait and not do anything before then. So that's why we're going to use VRO first.
Okay.
So we haven't thrown in the towel yet. We're still looking, still searching, and hoping there's another flyby there because it would be worth all that effort. So it's one of these things. It's kind of a high risk, extremely high reward scenarios that you just got to go for.
Gotta do it. Sometimes lightning strikes twice. Very cool. Mark, I want to thank you so much for sharing your article and the backstory of your discovery in the motion. It's very nice. Thank you.
My pleasure. Yeah, it was a great project.
And that will do, everyone. And I hope this made your cold Kuiper Belt day a little bit better. And we will see you on the next one. Bye-bye.
Bye.